所以我们上一次讲到第4章第9节的中间一小部分啊，我们大概把4至9讲完之后呢，4至10 further rotation 我也会讲，但是我会跳过4至11的 couple mode 的 analysis 啊，然后直接先教第7章啊，因为跟考试有关，跟这个期末考有关的部分，我先尽快先教，然后第7章教完7至3之后，我再回到第4章的 couple mode theory， 如果有时间的话啊。那因为我们只有16周，时间很短啊，所以我得教快一点。So today I continue to teach section 4.9 and section 4.10, and then I move to chapter 7. And after ending the teaching of chapter 7.3, then I will move back to teach 4.11 and 4.12 if I have enough time to do so. Okay, and the final exam will be held in 12月16号。December 16 will be the final exam. 好，那期中考下礼拜一定会发啊，会检讨啊。I will discuss review the middle exam, okay, next week. 好，然后我们现在就进入到这个上次还没讲完的4至9哈。So we have learned last week we wrote down this equation in the optically active medium. In optically active medium, we can write this result. We can write up this result. Here we have G cross E. This epsilon is the epsilon when optical activity is turned off. Okay, if there is no optical activity, then originally we have epsilon equal to this one, just like what we did before in chapter 4. Okay, and then if we turn on the optical activity, we have to consider this term. Okay, here G is a vector whose direction is the same as the direction of K. K is written as K times S unit vector, and G is equal to G times S unit vector. They direct to the same direction but have different magnitude. Okay, and then if we want to consider something like this, then we can rewrite this as this in the metric form. Here, A is defined as A3, A2 minus A2 minus A1, 0. Okay, so here we have the G vector. G matrix is defined according to the G vector. minus G3, G3 minus G2, G1, 0, G2 minus G1. Okay, this means that the 1,2 component is given by minus G3, which is equal to the minus 2, 1 component, etc. Okay. So we can write this relation between P and E as epsilon plus I epsilon 0 G matrix times E vector. Okay? And we can define this combination as epsilon prime. We can write this as epsilon prime times E. Here epsilon prime is nothing but epsilon plus I epsilon 0 G. Here epsilon is a matrix. This is also a matrix. That's it. Okay. So if you use this relation and discuss the modified Fresnel's equation of wave normal, you just substitute this D expression into Maxwell equation. We know that Maxwell equation, the Faraday's equation, induction law, this one, when we consider plane wave, it becomes K cross E equal to I omega mu H, okay, just like before. And we know that we have this Faraday's law. Faraday's law tells us that first, according to Faraday's law, we have this. And according to Ampere's law, we have this. Now we replace epsilon by epsilon prime. Okay? Then this tells us that K cross E is equal to I omega mu K cross H, and this is omega square mu epsilon prime times E. Okay? Then according to vector analysis, this is equal to K dot E times K minus K squared E equal to omega squared mu epsilon prime times E. Okay? And this means that you can write up this equation. Okay. You can write this as K squared E minus K dot E k plus omega squared mu epsilon prime times e equal to 0. Okay, just like we derived the Fresnel's equation with normal before, we can write down this equation as this one, ex, ey, and ez. Okay, here we have for the x component of this equation, we have k squared minus k这样吧，比如说 x component，for example x component we have k squared ex minus k dot e times kx, okay, plus the x component of this one. However, now since epsilon prime now becomes epsilon plus I epsilon 0 times g. So now epsilon prime is not a diagonal matrix. Okay, in the section 1 or 2, we have this epsilon a diagonal matrix, which means we work in the so-called principal axis. So this epsilon is a diagonal matrix. So in that case, the x component of this is just equal to omega squared mu epsilon x times ex. Okay. However, now since we have this term, this is no longer as simple as epsilon x times ex. Instead, we have a correction term here. So this becomes more complicated. However, we can still try to find a solution. We just add this indicates that the determinant of this matrix to be equal to 0. And this gives us the new modified Fresnel's equation with normal. Okay. And the result is this one. 这中间推导过程，其实我有写，我到时候再把这个参考的档案给大家。I have written a note for the derivation, but I will not correct this in this class. I will just send the files to you for your reference. Okay, and the final result is this: sx squared over nx n squared minus nx squared plus sy squared over n squared minus ny squared plus st squared over n squared minus nz squared minus 1 over n squared. And this is equal to g squared times nx squared sx squared plus ny squared sy squared plus nz squared sd squared over this one.就修正之后的 Fresnel's equation with normal surface 的这个方程式，从原来的这个直接等于它变成了减掉这个之后多这个项，这一项正于 g 平方啊。那这个东西呢，它的推导很麻烦，但是呢，它的应用呢其实并不难啊。The derivation is a little bit tedious, but its application is quite simple. I can multiply this factor, the denominator factor, to this equation. this result. A times n squared minus n1 squared. N squared minus n2 squared is equal to A times G squared. Here this A is just the leading coefficient of this equation. Okay? You multiply these factors to, suppose now we consider the situation that we turn off the optical activity. Okay? We have the original Brodell's equation or wave normal. Then we multiply this factor into this expression, we get the equation A n fourth power times B n squared plus C equal to 0. Okay, and we solve this to get to possible solution. Okay, we can find two possible, and the first one is n1 squared, and the second one n2 squared. This just expresses how we factorize this equation. We factor out this leading coefficient, and then the remaining term are n minus n1 squared times n minus n2 squared equal to 0. Okay, so its solution are n1 squared and n2 squared, and we can take the square root to get n1 and n2. Okay, and then we turn on this optical activity term, and we can find that the result is just this one. Here A is nothing but this nx squared sx squared plus ny squared sy squared plus nz squared sz squared. A is just this coefficient. Okay. And since A is not equal to 0, so we can conclude that after the multiplication of optical activity, the result becomes n minus n1 squared times n squared minus ny squared times n squared minus n2 squared is equal to g squared. Okay, so we can rewrite this complicated expression into this form. Okay, here n1 and n2 are the two eigenindices for the non-optical active crystal. Okay， 就是说我们把这个所谓光学活性关掉的时候，原来的那两个解出来的eigen index 就是这两个 n1 n2。好，我们重新把它拿来用的话，那在打开那个 optical activity 的时候，方程式就修正成这个样子啊。So this is equivalent to this equation. Okay. And so for the purpose of application, we usually consider the situation that the wave propagated along the z-axis, and the n1, n2 are two eigenindex corresponding to the x and the y-axis of this crystal. Okay. 好，那这个方程式呢，我们怎么去用它呢？是这样子的。Now I show you how to use this expression to find the new eigen polarization and the new eigenindices. Okay, and since G usually is a very, very small quantity. usually G is a very small quantity. Okay, so we can use this factor to discuss how to derive an approximate solution for dealing with this problem. Okay, suppose we have N1 equal to N2. Now we consider the situation. Suppose N1 is equal to N2 equal to N bar. Then we can discuss how to derive the modified N. Okay. In this case, we have N squared minus N bar squared equal to G squared. Okay. And then this means that N squared minus N bar squared equal to plus or minus G. So N squared becomes N bar squared plus or minus G. So we can take the root to find the two possible solutions of this new refractive indices. This can be rewritten as square root of this one, G plus or minus N bar squared. And since G is much more smaller than N bar squared, so we can apply the so-called binomial formula. Binomial formula means that this can be approximated by 1 plus minus G over 2 N bar squared. Okay, so this is N bar plus or minus G over 2 N bar。就如果这个量跟1比起来非常小的话，开根号就是相当于1去加后面这个东西乘上1/2。好，那所以呢就得到这样一个结果。好 ，so this means that say NL equal to N bar plus G over N bar and NR say equal to N bar minus G over 2 N bar. So what is the rotatory power? Rotatory power is equal to rho times pi over lambda times delta n. And now delta n is nothing but G over N bar. Okay, because now delta n is NL minus NR is equal to G over N bar. Okay. 好，这边其实究竟哪一个是 L， 哪一个是 R， 其实不一定，我这只是举例说明。好，那当然就是说这个电台可以正号或负号可能反过来，就你正号负号反过来。好，那就你就把左右边Here we have the difference between these two refractive indices equal to G over N bar. So we get rotatory power equal to pi G over lambda N bar. Okay. And in the textbook, the author also gives you an expression about this G. G is the magnitude of the G vector, which is given by linear sum of the S vector. 就是 S vector 乘上一些系数它都是二次方向或是双线性形式就加起来。 那这个部分的话呢，我没有办法去推导它。好，那这些东西的话，如果真的很想要很深入了解它的同学，可以去看，比如说从蓝到这个讲介质中的电磁学的第8册啊，可能可以找得到这个答案。但是呢，我们就不用花这个精神去看它，或者是 Bohr and Wolf 可能会有这个东西啊。You may find equation how to derive equation 4.9-15 and 16 in some advanced books such like Landau's theoretical series volume 8 or Bohr and Wolf 好，那这些部分我们就先略过然后直接走下面一步。下面一步是什么呢？就是说，我们这边只讨论最简单状况，就是 N1 跟 N2 本来是相同的。那如果 N1 跟 N2 并不相同的话，我们要怎么去讨论它？So now we consider the more general situation that if N1 is not equal to N2, then how can we proceed to find the eigen polarization and the eigen indices? Okay, so to do this, we need to find the inverse of the epsilon prime. This can be written as epsilon plus I epsilon 0 G times E, which can be written as epsilon prime times E. So you can write down E as epsilon prime inverse times D. In the textbook, the author writes this as 1 over epsilon prime, but remember that epsilon prime now is a matrix, so you had better write this as epsilon prime inverse instead of 1 over epsilon prime. Okay. And since we have these two equations, so we can write although we can use E vector as our variable, we can instead use D as our variable. So we need to rewrite E here as K cross epsilon prime inverse times D. Okay, equal to I omega mu H. So K cross epsilon prime inverse D is equal to I omega mu K cross H. And now K cross H is minus I omega times D. So this is equal to omega squared mu times D. Okay. And now we substitute this expression for K. K is equal to omega over C times N times S. Okay. N is the refractive index to be determined. Okay. So we substitute this into this equation. We get omega squared over C squared times N squared times S cross epsilon prime inverse D by epsilon 0. And now we compare the left-hand side and right-hand side. We see that if we multiply we define eta as epsilon 0 times epsilon inverse. And we define eta prime as epsilon 0 times epsilon prime inverse. Okay? And then this tells us that omega squared over c squared n squared times s cross epsilon 0 times epsilon prime inverse, which is equal to eta prime times d, is equal to omega squared times mu epsilon 0 times d. However, we approximate mu by mu 0, and this gives us 1 over c squared. Okay, so both the left-hand side and right-hand side have this factor 1 over c squared and omega squared. So we have this result: n squared s cross eta prime d is equal to d. Okay, or s cross eta prime d is equal to 1 over n squared d. Okay, we have already encountered a similar equation when we discussed the index sinusoid. Okay, so we can just like we did before, we replace G cross this operation. We replace G cross by G matrix. Now we can replace S cross by S matrix. Okay, here the S matrix is nothing but this. This, okay? So this means that S matrix times eta prime d is equal to 1 over n squared d. Okay? So if we try to calculate this, we see that usually for convenience, we will choose S to be along the third direction. So only S3 equal to 1 and S1, S2 are equal to 0. Then this will become only the 2 by 2 part is useful. Okay. Before doing so, I just try to explain to you how to find an approximate expression for eta prime 啊，就是说我们后续当然是可以探讨这个这个啊，就是如果是只有 S3等于1，然后 S1、S2都是0的情况下啊，会怎么化解这个问题？但是在做那一步之前呢，我们需要去讨论eta prime 怎么算啊 ？eta prime 是原来的 eta 是 epsilon 0乘上 epsilon 负1次方，新的 eta 呢 eta prime 呢是 epsilon 0乘上 epsilon prime 的负1次方。那 epsilon prime 有一个互相拿来捣蛋的那部分，就是不是只有 diagonal 很简单啊 ，diagonal 的部分非常简单，但是它有 off diagonal 的部分，就是那个 G 矩阵跑进去了啊。那我们所知道的是 G 矩阵的影响很小，但是我们还是要知道怎么去计算这个影响，所以我们就需要知道说，假设我不要一个完全精确的公式，因为太复杂，但是我要一个够精确的近似公式啊，那我们就想要去探讨这个 eta prime 的近似公式会长成什么样子。OK， although in principle, we can do all these things by numerical method very accurately. Okay. However, it usually is more convenient to discuss how to derive an approximate expression for eta prime if we assume G matrix is small enough. OK 啊，我们怎么样去决定所谓的 G 矩阵够小的？这个矩阵怎么比大小？这个其实没有一个规则哈，但是可以这样想象，就是说，如果你去计算 G 矩阵 eigenvalue， 这 eigenvalue 每一个都比 epsilon 负1次方 eigenvalue 小很多。那我们就当做所谓的 G 矩阵很小 ，OK， 然后我们就可以用它很小这个事实去找到近似解啊，eta prime 的近似解啊we will assume that the G matrix has eigenvalues much more smaller than the eigenvalues of epsilon inverse, okay, and then we can find the approximate expression for this eta prime matrix. Okay. To simplify our formulation,好，那怎么去做到这一点呢？你可以这样想哦，我们想象说有两个矩阵哈 we discuss this by this consideration. Suppose we have two matrices A and B. A and B are two matrices. And suppose the determinant, every eigenvalue of B is much smaller than any eigenvalue of A. Then if we need to consider a new matrix C is equal to A plus B, A plus B, and the B is much smaller than A. Then how to find C inverse? Okay. We want to find the inverse of A plus B. Okay. And then we can write this as this one. Okay. A times unit matrix gives us A times B, A inverse gives us B. And we have two matrices multiplication and take the inverse of the whole. And according to linear algebra, we know that if we have two matrices A times B, we take the inverse of them, the multiplication, it is equal to B inverse times A inverse. Okay? And here, this is A, this is the B. So this is A inverse times the inverse of I plus B A inverse. OK？ 好，为什么我需要特别弄出一个单位矩阵呢？因为单位矩阵有一个特色，单位矩阵跟任何矩阵都互相 commute。好，我们知道 in general 矩阵 A 乘以 B 不等于 B 乘以 A， 但是单位矩阵乘任何矩阵都可以跟它 commute。所以意思就是说，当你把单位矩阵跟别的矩阵加在一起，你要去处理它的什么东西时候，你完全可以把后面的矩阵当成一般数字在处理，不用考虑什么矩阵不能 commute 的问题。好，所以呢，这个东西的负一次方，我们现在假设这个比单位矩阵小很多，好，就说就是这些东西，它的 eigenvalue 会比单位矩阵小很多，我就可以把它当成什么一般数字去展开，就是说我好像一去加一个微小量，然后取负一次方，所以这个就会变成这样。Okay? Because now every term commute with unit matrix. Okay. So if I keep up only to this term and ignore the higher order term, then I can approximate the result as. So now can be So now C can be approximated by A inverse times 1 unit matrix minus B A inverse. Okay, so this is equal to A inverse minus B A inverse B A inverse. Okay. This is approximated expression. Okay. So if we apply this formula to our eta prime, remember now eta prime is eta eta prime now is this inverse epsilon 0 epsilon prime inverse. Okay, and what is epsilon prime? Here, epsilon prime, epsilon 不对啊，应该是这样吧，这样子。Epsilon 0 times epsilon prime inverse. Okay, and this is epsilon 0 times epsilon plus I epsilon 0 G inverse. Okay. And you can treat this as A, this as B, then this becomes epsilon 0 times epsilon inverse minus epsilon inverse times I epsilon 0 G epsilon inverse. This one. Okay? And epsilon 0 times epsilon inverse gives us eta. And now we have epsilon 0 times epsilon inverse. And this one, epsilon 0 times epsilon inverse. So we have 2 eta minus I eta G eta. OK。好，所以我们就把 epsilon prime 的近似式写出来了嘛。So now epsilon prime can be approximated by this expression, eta minus I eta G eta. OK， 好，这就是我们所找到的近似表达式。好，那这个近似表达式呢，我们就可以拿来用了。好，我们现在就拿来用，是吧？ So now we have this S times eta minus I eta G eta times D equal to 1 over n squared D. So now if we choose S to be along the third direction, only S3 survive, then S times S becomes this one. We can try to calculate the result. Okay. And so only the first two terms are useful. And similarly for eta. Although originally we have eta as a 3 by 3 matrix, but now we can use only the 2 by 2 part. Eta is originally this one, and this part, this 2 by 2 part, is the so-called eta t. Okay, so we can replace this as minus eta t minus I eta t G t eta t times d equal to 1 over n squared times d. Here d is written as d1, d2, only 2 components. 好，那我们下一堂课呢，再来好好讨论这个问题。我们这边先休息一下，先暂停一下。好 ，OK。That's how to solve this problem. We choose the S to be along the third axis, okay? And then since D vector is perpendicular to the K vector, so D has first and second components, but D has no the third component. Okay, and then in this case, only the 2 by 2 part of eta matrix are useful. And so we can write this as, and you can check that under this situation. S times S is equal to minus 1, 1, 0. This diagonal matrix. So you can replace this as, you can replace S as the 2 by 2 matrix, and you can check that the square of this x is minus 2 by 2 unit matrix. Okay? And so you can write this result as eta t minus I eta t g 2 by 2 eta t times d is equal to minus 1 over n squared times d. Okay, and if we choose the propagation to be along the third direction, the third axis, then this eta t represents the eta that without this optical activity. So we know that the original epsilon is equal to epsilon 0 times n1 squared, n2 squared, n3 squared. Okay. Here 1, 2, 3 are just the principal index。这个就是原来的 nx、ny、nz 了。只不过现在的 x、y、b 变成是1、2、3就是。So according to this result, we know that epsilon inverse is epsilon 0 times 1 over n1 squared, 0, 0. 1 over n2 squared, 0. 1 over n3 squared. Okay? Inverse. Okay. So this means that the original eta is this, which means that eta t is this. Okay? 所以 eta t 就是什么东西？ So this means that eta t is 1 over n1 squared, 0, 0, 1 over n2 squared. And now g, the 2 by 2 g is nothing but this minus g, 0. Okay? So this is the eta prime. So what is eta prime now? Eta prime is now equal to 1 over n1 squared, 0, 0, 1 over n2 squared, minus I 1 over n1 squared, 0, 0, 1 over n2 squared, times 0 minus g, 0, 1 over n1 squared, 0, 0, 1 over n2 squared. Okay. And the result is this one. 1 over n1 squared. IG over n1 squared, n2 squared, minus IG over n1 squared, n2 squared. 1 over n2 squared. Okay, this is the eta prime. So now we solve the equation.这边其实应该叫做 eta prime t。So now we have eta prime t times d times d。看一下啊，这边决定对不对？刚刚的好，我刚刚在推导的时候，有个地方负号少写了，所以这边其实正的啊。Here is positive sign， OK， 回去 check 前面的啊，这边是正号才对啊。So we want to solve this equation. Eta prime t times d is equal to n1 over n squared times d. This means that 1 over n squared is the eigenvalue of this eta prime t. So this means that we need to solve for this ig over n1 squared, n2 squared, minus ig over n1 squared, n2 squared. 1 over n2 squared minus 1 over n squared times d1 d2. Okay. 好，我们原来用这个伊塔 t 的时候呢，代表的是我们原来有两个分量两个解啊，一个叫 d1 呢是10，另外一个叫 d2 呢是我们把它写成01啊，然后这个东西是对应到原来的伊塔 t 的。那我们现在的情况是对应到伊塔 t prime， 伊塔 t prime 呢会 d 就会等于什么呢？ d1 的小写的 d1 加上 d2 的小写的 d2，OK， 也就是 d1 d2。Originally, if we have no optical activity, if the medium is not optically active, then originally we have eta t times d equal to 1 over n1 squared times d1, eta t d2, 1 over n2 squared d2. Okay? And if we choose our coordinate axis to be along these two eigenvectors, then we can write d1 as 1, 0, and d2 as 0, 1. Then this eta t matrix becomes diagonal form. Okay? And then we use this basis to discuss what's the influence of the optical activity. Now we turn on the optical activity, then we need to solve this problem, this eigenvalue problem. Now, in terms of these two basis vectors, the new d vector can be written as d1 times d1 vector plus d2 times d2 vector, which is equal to d1 d2 column vector. Okay. So, what's the eigenvalue of this equation? It's very easy. We see that it's equal to n 1 over both power of n minus 1 over n1 squared plus 1 over n2 squared times 1 over n squared plus 1 over n1 squared, 1 over n2 squared, minus g squared over 1 over n1 both power, n2 both power equal to 0. Okay? So the solution for 1 over n squared is this one. Okay. This one. So this becomes this. Okay, so this is the solution of 1 over n squared under the influence of optical activity effect. 所以现在在这个光学活性的影响下 ，n 被修正成这个样子啊 ，n 被修正成。那 n 被修正成这样的时候呢，你要解出这个 eigenvector 的话呢，你怎么去解这 eigenvector？ 其实很简单，就是说，你现在是这个 eigenvector now is described by 你可以用这个去乘它，要得到0，啊，所以这个去乘这个要得到0 ，so minus ig over n1 square n2 square times d1 plus 1 over n2 square minus 1 over n square times d2 is equal to 0. So this means that d1 over d2 is minus这个拿进去就变成is equal to this. So we can choose this as the d1 component and this as the d2 component. Okay. So what is this? If you try to 这边去解 subtract 1 over n2 squared, this becomes 1 over n1 squared minus 1 over n2 squared. that the Jones vector for this D vector now becomes 这是没有 normalize 的你可以再 normalize， 如果需要的话。Okay. So the new eigenpolarization becomes this form. And you can see that if G is equal to 0, this is linear polarization. However, if G is not equal to 0, this becomes an elliptical polarized line. This is an elliptical polarization. 这是一个椭圆偏振也就是说呢，本来是这样子originally 这个方向就是 D1 的方向，这个方向就是 D2 的方向。Okay. Before we turn on this optical activity, the line polarized along D1 or D2 both are linearly polarized line, linear polarization. Okay. When we turn on the optical activity, it becomes we get two possible elliptical polarization. Okay. 但是呢，这个图是画的比较夸张的，实际上这个椭圆非常非常低In fact, this ellipse looks just like a line segment because this height is very narrow compared to the major axis. The minor axis is much smaller than the major axis. So although it is an ellipse, but it looks just like a line segment. 就是好像一个线段一样就是说它其实看起来还是非常像原来的线列阵但它的确因为 optical activity 影响而产生了一个小小的分量，让它变成椭圆偏振只是椭圆非常扁。你不仔细看它还是线列阵但你仔细看，你发现它是椭圆偏振好，那什么是它的这个叫做 ellipticity? So the ellipticity is just the ratio between this and this. 然后你可以自己把它这个写一下就是4.9是29那我们现在来讨论一个 special case 就是说，虽然我这边讲说被 optical activity 影响的线偏振变成椭圆偏振，但是椭圆非常扁，看起来还是跟线偏振非常像但差一点点而已但是有一个特殊状况是会让它完全变掉，什么情况呢？就是原来的 N1 跟 2如果根本就相同的话，就是所谓的 isotropic 或者是完全相等的时候，这时候呢，它就会是两个圆偏振Now we consider a special case that if now N1 is equal to N2. If N1 is equal to N2, then you substitute N1 equals N2 equal to N bar into this equation. You see that here this becomes 0, this becomes 0, and the J plus minus now becomes this one. Yes, it's a. So we can factor out this G over N1 squared, N2 squared. And the remaining terms are 1 plus minus I. Okay? This factor is not important, it's irrelevant. Okay? Because when we judge the polarization, we just see the relative components of these two 那所以你从这里看起来，这个就是两个圆边阵So these are right hand circularly polarized line and left hand circularly polarized line 所以如果是 N1 N2 完全相同的时候，它其实就会得到两个圆边阵，跟我们原来讨论的一样就是 just like we discussed before 那好，接下来我们来看4至10节讲一个叫 Friday rotation 它的效果也是产生一个从线边阵变成椭圆边阵或圆边阵的变成圆边阵的结果嘛其实是直接变成圆边阵但是它的产生机制呢，跟我之前介绍的不一样。我们之前介绍的这个 optical activity 是因为分子的结构本身有一些，比如说螺旋形或左右手不同造成的。那现在所谓的 Faraday rotation， 它是因为加磁场而造成Now we discuss another mechanism which causes the polarization to change from elliptical to circular, from linear polarization to circular polarization. This mechanism is called Faraday's rotation. The underlying physics is that we apply magnetic field to the medium. So the spin or electron motion will be influenced by the applied magnetic field. So now we still can write down a G vector. But now the G vector is determined by some constant times the magnetic field. OK， 就是说现在的这个 G vector 呢，它不再是根据 K vector 来定，而是根据 B vector 来定就是根据磁场来定now G vector is determined by the applied magnetic field. This leads to some interesting results that originally in the case that optical activity was induced by chirality of molecule, we have the property that suppose this is a optically active medium. Here we have a mirror. For the original case, if you consider wave propagate along this direction and then reflect back by the mirror, then the polarization will be modified back to the original polarization. 就是说，我们在原来的 optical activity 的时候你 正的走一次，反的再走一次，它会回到原来的 polarization。但是呢 ，Faraday rotation 会不一样。你顺着磁场走一次，然后再反过来再走一次呢，你得到的是累积的结果，啊，变成 double 转的 double 的结果，啊 ，double 的角度，啊，这个原因是因为在原来前面那种 case 里面，你正的转一次，正的走一次时候，你的 k 是朝这，你反过来的 k 是反过来的，所以就抵消掉了。但现在呢，你正的走跟反的走，你的磁场都朝同一个方向，所以没有抵消，啊，会变成2倍，啊。So, in the previous case of optical activity, when you when you replace the original propagation direction to its opposite direction, the k vector becomes its negative counterpart, and then the total aggregation of the polarization change becomes 0. However, for Faraday rotation, since the g vector is determined by the b vector, and the b vector is fixed to a certain direction. So, if you have a wave propagate along this direction and reflected back by a mirror, then the total rotation becomes double. OK， 啊，变成2倍，啊，会跟那个原来的那个不一样。好，那如果出现这个 Faraday rotation 的时候，啊，那这边就是不同材料会有不同的伽马，这个伽马呢，不同，然后我们可以把这个 rotatory power 写成叫 V 乘以 V， 啊 ，the rotatory power can be written as V times V. V is the magnetic field. Magnetic induction。好，我们还是把 B 叫 magnetic induction， 然后呢，这个 H 叫做 magnetic field。那这个 V 呢是有一个称呼呢，叫 Verdet constant。Verdet constant。这个是有一个表啊，课本有一个表列出这些不同材料的 Verdet constant 啊，大家可以自己参考一下。好，我们讲到这边的时候呢，我们后面那个 couple mode 我们就暂时先略过，我们直接先跳到第7道去讲啊，因为我们先把我们主要考试会考到的部分先讲啊。So now we move to chapter 7. 因为这学期实在太短了，我实在太不适应这个16周啊，那所以还是赶快把能教的部分赶快先教一下。好，如果你们愿意听，我要教30周，我也愿意啊，但是没办法，就是这样啊。好。In chapter 7, EO effect. Electro optics. 好，我们到目前为止，我们看到就是说，这个晶体材料呢，它的这个特性呢。可以有很多方式的应用，或是去影响它。好，比如说加磁场 Faraday rotation 刚刚讲，好，可以去影响它。然后呢，或者是这个你其实用了比如说这个不同的轴向的wave plane 的去排，然后你可以用它来做一些事情。但这些东西的话呢，其实就是你做的这些调整呢，都没有去影响到这个折射率本身。啊，那实际上呢，折射率是有可能被外加电场所影响。啊， 它影响的非常小。那这部分属于这个非线性光学啊 ，non-linear optics. Okay. When you apply electric field to some material, then the charge distribution of this material will be influenced by the applied field. Okay, and the so-called electron cloud being distorted, okay, to different shape, and all this, in fact, can influence a little bit the magnitude of the refracting index. Okay. So now, if we consider the influence of the refracting index, then we go to the region of so-called nonlinear optics. 在我们原来的这个电磁学里面，我们通常都不去考虑这一块啊，因为电磁场，我们通常考虑的电磁场太弱了，它对于这个折射率的影响非常的小啊，非常小，所以我们可以忽略它。但是如果你加的这个电场够大的时候，其实这一些折射率是会被影响，好，会让它的值有一些少许的变化。好，那把这部分考虑进去，就变成非线性光学。好，然后非线性光学里面呢，我们在这本书里面应用，我们主要考虑所谓电光效应，不是那种非常极端的非线性的东西，而是我们只是让折射率被外加的电场影响一点点，然后去看如何通过外加电场的影响去控制折射率，然后来做一些有用的事情。好 ，So we discussed how the applied electric field will modify a little bit the refracting indices, and how to use this modification to do something useful. Okay. 这里面有所谓的电光效应啊，那这个电光效应呢，分成线性跟非线跟这个二次方的啊，一次方跟二次方啊，linear 一次方的啊 ，linear electro optic effect is named as focus effect. Quadratic is called Kerr effect. OK， 好，那我们基本上是集中在这两个啊，就是说一个叫 Perkins effect， 一个叫 Kerr effect。好，那Perkins effect 跟 Kerr effect， 你合起来讲的话，你可以这样想，就是说。Consider the index ellipsoid. Originally, if there are no EO effect, then the index ellipsoid can be written as this one. Okay, we can use the index ellipsoid to find the polarization of the light and the propagation direction and how to predict the phase of the polarization state. Okay, and 我们这边 们从前有两种方式可以来讨论这个光的辩证状态，一种是所谓 normal surface， 那个是集中在这个k 空间中，重点是看 k vector 本身。但是呢，有另外一种描述方式呢，是看 d vector， 就是这个所谓 index result。OK， 我们在这个第4章时候也提过它。那原来呢会长成这样。So we have two possible ways to describe to study the propagation of wave inside the crystal. The first one, we use the so-called normal surface Linear's equation of wave normal. The second method is to consider the d vector instead of k vector. Then the equation describing the d vector is called index ellipsoid, which can be written like this. Here, x, y, z are the normalized d vector. X, y, z are in fact this one. Here, UE is the energy density of electric field. 就是说你把那个电磁场里面的电场所储存的能量叫做 UE 的话，你把这个东西除以它，就会定成这三个分量叫 x, y, z。那这样子的equation叫做 index ellipsoid。好，那我们现在要看的是，如果我加一个外加的电场够强，去影响这些折射率的时候，那这个 index ellipsoid 就会变了。它就会变，怎么变呢？它有两种变的方式，一种是它的这个形状呢，可能长短会有一些收缩；另外一个是它的方向可能会有点旋转。OK， 好，所以这两个东西会变。那这个东西的变会反映在什么东西上呢？我们刚刚一直在讨论一个叫做伊塔这个矩阵，对不对？这伊塔呢其实是有名称的这个 this equation in general can be written as eta ij times xi times xj sum over ij equal to 1. Okay, j runs from 1 to 3. I also runs from 1 to 3. Okay. 你也可以用这个爱因斯坦 convention 把这个 convention 符号省略掉，直接写成这样。Use the Einstein convention, we can ignore this notation, this summation notation, and just write the result like this. And this is just this equation in arbitrary coordinate system. Okay. So now we discuss what is the influence of the applied electric field. We originally have eta ij of 0. Then we apply electric field E to find the final eta ij of E. Okay. This modification was called by Perkins effect or Kerr effect. Okay. So this means that eta ij are functions of E vector. So we can parallel expand eta ij. 我们可以从它的泰勒展开始。We can parallel expand eta ij as originally we have eta ij 0 plus rij k ek plus sij kl ek el。OK， 这意思就是说，我会有电场1次方跟电场2次方去影响这个伊塔。好，然后这边是 sum over k， 这是 sum over k 跟 l， 就是1、2、3分量把它加起来。这边有一些系数，这些系数，这些系数呢，其实就是相当于是从伊塔的泰勒展开始去得到。好 ，So you can treat this as the Taylor extension of the eta function, which is the function of E vector. E vector has 3 components, 1, 2, E1, E2, E3. So here we have some coefficient multiplied to every component and sum them over. And then this I, J, K give us percussive vector. And this S, I, J, K, L give us curly vector. So after we apply the electric field, the external electric field, then the original index sinusoidal now becomes theta ij e times xi xj equals 1. Okay. Which means that we can write this as x, y, z times this x, y, z equals to 1. Here, the matrix in between is eta ij of e. So our task is to diagonalize this eta, new eta matrix, to find the new principal axis. Okay, so then we can find the new principal axis and the new refractive indices. 就是我们加了这些修正之后因为外加的电场就导致修正之后，我们的伊塔变了。那我们的伊塔变了，假设我原来的伊塔是 diagonal 的，我有这个 nx、ny、nz， 然后呢，但是我加了这个修正之后呢，它变成 off diagonal 那它会有这个 off diagonal 分量，那我就要想办法把它重新 diagonalize， 然后变成新的这些 diagonal 形式，那顺便就找到新的主轴找到新的主轴。所以第7章其实就在讲这件事情So in chapter 7, our purpose is to study how to find the new principal axis and the new refracting indices if we apply the electric field. 那这边再稍微提一下，就是说这里的这个电场指的究竟是什么？我们知道电磁波本身就有电场那这个电场跟电磁波电场其实是混在一起的，但是呢，我们这边的基本假设就是我们电磁波那个电场跟我们外加电场比起来弱很多，所以这边的电场指的主要就是外加的电场。就是 in fact, the material cannot distinguish which part of the electric field was from electromagnetic wave and which part is from the externally applied static electric field. However, we usually assume that the electric field from the light itself is much weaker than the applied external field. So when we discuss the influence to eta, we can assume this E vector are just the E from the externally applied field. OK， 就我们这个强度上有很大的落差就是其实是主要是把它当成是我们外加的这个电场好，那除了这个之外呢，还有就是课本有提到有另外一种表达 equation can also be written as Fijkpk plus Gijkl pkbl. And you can find the relation between these two kinds of expression. It's easy to derive this result because you know that D is related to E这边没有加都上 and which is equal to epsilon 0 times EK plus EK. So this means that PK is epsilon k minus epsilon 0 times EK. Okay, so you can also write EK as PK over epsilon k minus epsilon 0. So you just substitute this expression here, then identify the result as this result, then you get this relation, this two relation. Okay. 好，那我们这边先休息一下，下堂课再继续。那我们现在来讨论一下这个东西的对称性啊。So now we consider the symmetry of these two kinds of coefficients. According to this expression, you can treat this as, you see that we use this eta ij to multiply xi and xj sum over to get 1. Okay? So this means that if we replace I by j, we can write this as xj xi. So, and this is just equal to this one. Okay, because I and j are dummy index. Dummy means that you sum over all possible components. So we can conclude from this expression that eta ij can be chosen to be eta ji. Eta ij is equal to eta ji. So this property implies that eta ij, if eta ij is equal to eta ji, then this implies that Rijk is equal to Rjik. Okay, we can exchange the order of I and j without changing the result. Okay. And similarly, we see Sijkl is equal to Sij J I K L. The reason is the same as R I J K equal to R J I K. Okay. However, we still have the possibility that we can change K and L because we can change the order of K and E L without changing the result. So this means that S I J K L is equal to S I J L K。就是我们那个这边的三只角呢，前两只可以交换而不改变结果，而这个四只角的呢，前两只交换不改变结果，后两只交换也不改变结果。好，但是你不能把第二只跟第三只交换，它会变的它结果会不一样但是呢，前两只交换结果跟后两只交换结果是不会改变结果是不会改变结果。那根据这个特性呢，我们就可以大大的减少独立分量的个数就是说原来的 RIJK 看起来有27个分量，因为3个 I 3个 J 3个 K 嘛，3加3就27嘛。可是现在如果前两个可以互换而不改变结果，我们就不要那么多了，因为重复的就当做一个就好。OK， 所以呢，这个代表的意思是什么呢？就是我们可以重新去编号它们，而让整个结构写起来更简单。So, the symmetry that we can exchange the indices implies that we can replace the original index by some new design indices, so that make the independent components fewer, OK， 变得更少那这个的意思就是说，比如说这边的 IJK IJ， 既然 IJ 等于 JI， 所以我们可以这么做We can rename 1 as 1, 2 as 2, 3 and here rename as 3， 这都没问题，因为这两个本来就重复的。然后呢，我们可以把这个31好，23好，23呢跟32重新命名叫做4，好，然后13跟31呢重新命名叫做，然后这个12跟21重新命名叫做这个。We can rename the indices. This is easy to remember. 1, 2, 3. How to memorize this? My method. I plot this figure. One, 2, 3. Okay. Then 2, 3 correspond to 1, and I plus it. Add 3 to get 4. And we have this 4. Okay. And 1, 3 or 3, 1. 3, 1, 2. 2 plus 3 equal to 5. And 1, 2, 3. 3 plus 3 equal to 6。这是我的记忆方法但你们不一定要这样记，我可以自己想一个方式So here So RIJK, originally we have 3 times 3 times 3 equal to 27 components. Now reduced to the IJ pair 1, 2, 3, 4, 5, 6. This becomes 6 and 3. So only 18 independent components need to be collected. OK 就是它的独立分量其实只有18RIJK 是有18个独立分量。Similarly, for the SIJKL coefficient, originally we have 3 times 3 times 3 times 3, which is 81 components. However, the first two index, the independent components for first two index are only 6, and the independent component for the second pair are also 6, which give us 36. So totally we have 36 independent components. So 就是这个 RIJK 的系数其实只有18个独立分量，而 SIJK 呢只有36个独立分量。那所以我们就可以把它写成这样，就是说 ，suppose I write this as RAK or SAB. Okay. Now A takes 6 possible values and K takes 3 possible values. Okay. And here we have 6. Okay. 所以这个意思就是说呢，我们可以把这个 RIJK 呢写成一个矩阵你去查表的时候when you check the RIJK coefficient table, you see the result like this. R11, R12, R13, R21, 22, 23, R31, 32, 33. Okay. 41, 42, 43, 51, 52, 53, 61, 62, 63. 它是一个写起来就是一个6乘3的矩阵6 by 3 matrix. Okay, and we can see that the S coefficient can be written as a 6 by 6 matrix. Okay, 好，看起来好像这些分量很多，但大部分是0为什么大部分是0呢？这个东西可以经过进一步分析，去发现大部分分量是0原因是呢，真实的晶体之中它有很多的其他的对称性那这些对称性呢，如果用群论去研究它的时候，你就会发现呢，它有一些分量一定是一定是0那至于群论怎么得到这结论呢？我们就这门课就不用去管它其实在7至2有稍微提到一下，就是比如说有反射对称性For example, if the medium, the structure, the atomic or ionic structure of the medium has reflection symmetry, which means if we replace the original axis by its reverse, then we see the same structure then this will give us 0 RIJK 啊 ，because 你看啊，因为这个是给 x 分量，是给 y 分量，是给 z 分量啊。比如说3个轴，然后呢，你只要把它反转，它就要变一个负号，但是问题是它看起来又完全一样，它又不该变负号。就一个东西既等于自己的负号，又等于自己，那它就只能是0，所以这时候它就会变成啊，就说 if some coefficient reflect the way we represent how to denote the axis, then if we change x-axis to minus x, okay, then this RIJK becomes minus RIJK. However, you see the same structure, okay? So R minus RIJK must be equal to RIJK itself. So only 0 can equal to its minus. Okay, so this means RIJK is 0. 啊，就是如果是在这种情况下，内线分量就会是0。啊，那这只是一件很简单的考量，但是真正复杂的是在所谓群论。There is mathematics called group theory. Some experts can apply some theorem or some method in group theory to study the symmetry of the crystal. And then they can conclude that some components become 0. So if we check the table about RAK, then you see most of the components are 0. Only a few components left. 就只剩下一些少数的不为0的这个分量留下来。好，那我们就继续讲下去哈。就继续讲下去的时候呢，我们就来举具体的例子啊。好。好，我们现在来按照这个符号呢，来先考虑 Perkins effect。Now we consider the linear EO effect, the Perkins effect. Okay. So originally we have this equal to 1. Now we consider the modification. The modification, we have this R1 K. 1 means 1 1, so it times. ，K， 等一下，不是，等一下，不是，对，好，这样子，我重新这样写好。我们加上电场之后会被改成这样。After we apply the electric field, the index ellipsoid becomes this form. 地方写错，等号右边课本写成0，这是错的啊，是1。好 ，you can check in your textbook the right hand side is equal to 1, not is equal to 0. Okay? And here 1 means 1 means 1 means x squared. Okay, and for linear EO effect, we have k times some index k, so we have R1 k ek. Okay, and 2 means 2 means y. So here we have y, and here we also have the summation of R2k times ek. And 第三个其实是3了，这边写错了。3 means z, okay, and sum over k ek. And how about yz? We have two terms corresponding to yz. We have yz and zy, so here we have factor 2. And the yz means 2, 3. We see 2, 3 goes to 1, and 1 plus 3 gives us 4. So here we have the index 4. Okay, 4 corresponds to yz and zy. And now ek sum over with R4k. Okay, and how about zx? zx 3, 1, 2 plus 3 equal to 5. So here we have 5 times this. And do not forget this factor 2 because we have zx and xz. And finally, 1, 2, 3 plus 3 equal to 6. Okay, 1, 2, and 2, 1. So factor 2 and 6. And the sum over k, ek. Okay. 好，所以我们的这个线性的 EO effect 的新的index result 在加电场时候就长这样。好，然后我们的现在就要挑一些特例来看怎么处理。So in general, for linear EO effect, we have the modified index result look like this. And now we study some specific examples. The first example, we studied KH2PO4.叫 KBP 晶体，简称 KBP 晶体，它叫 KH2PO4。然后你去看它的这个它所对应到的课本上讲到它所对应到的symmetry 4/2，4/2M，这些都是群论里面的符号了4/2M 是群表示论里面的符号the notation from group representation theory and group theory. You do not need to understand this notation. You just check the table corresponding to this symmetry. So you can see that the result is tetragonal crystal. So the result is the R coefficient now becomes this one. Here we have 0, R4, 1, 0, 0, R4, 1, 0, 0, 0, R6, 3. Okay. Here you see that at this position, this coefficient is in fact 5, 2. This position, in fact, corresponds to R5, 2. But its value, according to group theory, we can conclude that it takes the value the same as R41。好，就根据群论可以算出来 ，R52会等于 R41。好，就是说虽然这边写 R41，但是你在乘的时候你要小心，它要乘谁？它不是乘 R41要乘的东西，它是要乘 R52要去乘的东西。虽然它的数值上是 R41。OK， 好，所以你这边就去小心。好 ，So now we see that there we do not have this, these are absent 好，然后呢 R41好，这边的话就变成 4, 1，因为只有 R 这边是 R41嘛 ，1 means x，OK，and R52的时候，这边是52嘛，我看到52分量没有，不是0嘛，这边52，所以这是 EY 嘛，但是它的数值等于 R41， 对不对？好，然后这个呢，最后这是 R63，这边只有0分的 ，OK。So we see now we have the diagonal part has not been keep the same, but the off diagonal part be modified. Here we have R41 times EX, and R52 taking value equal to R41 times EY, because now EY follow this index 2, OK。好，那如果你觉得这还很容易错的话，你可以用一个方式这么看啊，就是你怎么看呢？你可以这样想。We can write this as EX, EY, EZ, X squared, Y squared, Z squared, 2YZ, 2ZX, 2XY. Okay? You can write this, and you see now EX times R41 times 2YZ. Okay? And EY times R41 times 2ZX. Okay? And EZ times R63 times 2XY. OK， 好，所以就可以把那个修正项的部分，把它很顺利的写下来啊，你就这样写啊，就是你把这个 R 矩阵写好之后，这边写啊，上面 EX、EY， 这边是 X 平方、Y 平方、Z 平方，或者 2YZ、2ZX、2XY， 啊，这样你就不会搞错，就不会啊。好，那我们现在来具体看一下这个要怎么弄啊。So now we have x squared over nx squared plus y squared over ny squared plus z squared over nz squared plus 2R41 times EX YZ plus 2R41. In fact, it is R52 times EY XZ, and then plus 2R63 times EZ XY equal to 1. Okay. Now we consider two special cases. We consider first case 1. Case 1, we choose Ex and Ey to be 0. And Ec is not equal to 0. Okay. Which means we apply the electric field along the z-axis. Then under this assumption, we see that the index ellipsoid now becomes, and we know now we have for this uniaxial crystal, we have nx is equal to my equal to. Now we have nx equal to ny equal to no, and Ec is equal to Ne. So this becomes x squared plus y squared over no squared plus z squared over ne squared plus we now apply the electric field along the z-axis. So we have R6, 3, 2, R6, 3, EC, XY equal to 1。好，那这个情形是比较简单的，因为呢，在我们原来的这个 x 跟 y 的系数呢，大家一样。好，那这边出现了一个交叉项。那你要重新把它带入来，其实相当的简单，相当简单那你只要转45度就可以，就绕着自己走转45度，就可以把它带入来，那这个方法是这样So we can rotate the axis so that we rotate from x, y, z to x prime, y prime, z prime, which is equal to r of phi times x, y, z. Okay. If the rotation is 2D, which means that we rotate it with respect to the z-axis, then we can write this x prime, y prime as r phi 2 by 2 times xy. And we can rewrite xy as r inverse 2 by 2 times x prime, y prime. Okay. We can choose phi to be 1/4 pi. Okay. And so we can write this as this. This means that we can substitute x can be written as y can be written as then you can check that x squared plus y squared is the same as x prime squared times plus y prime squared. However, there is also xy. So xy now can be written as 1/2 x prime squared minus y prime squared. Okay. So now we have this. squared plus y prime squared over NO squared, okay, plus z squared over NE squared plus 这边换成2xy 就没有这个2分之一啊，然后就会变成 r63。So we have r63 EC times x prime squared minus y prime squared equal to 1. So this means that we have 1 over NO squared plus 63 EC times x prime squared plus 1 over NO squared minus 63 EC times y prime squared plus z squared over NE squared equal to 1. So now we can rewrite this equation as this form. Okay, which means that now we have 1 over nx squared equal to 1 over NO squared plus r63 EC, and 1 over ny squared is equal to 1 over NO squared minus r63 EC, and 1 over EC squared is just the original 1 over EO squared. 所以这样我们就可以把新的 nx、ny、nz 给造出来，是新的轴也已经知道，就是我们转45度So now we can find nx, ny, and nz according to this result, and we also have already know that the new coordinate axis, the new principal axis are obtained by rotating the x and y axis around the z axis by 45 degrees. Okay, 好。那但是呢，我们有时候会希望得到一个比较干净的近似解。好，就是你这当然可以解出 nx 跟 y， 但这个一堆根号其实不是很好用啊。那有时候我们为了要后续的讨论方便呢，我们需要一个比较干净的表达方式。好，什么叫干净的表达方式呢？就是我不需要完全100%精准，但是够精确，好，然后但是写起来比较简单，好，那答案是这样啊。我先把结果写出来 ，nx 呢可以写成 no 呢减1/2 no3次方 r63。然后呢，这个 ny 可以写成 no 加2/3 no3次方 r63。nc 就没问题了 ，nc 就是原来的。We can replace the exact result by this approximate result. Okay, how to understand this approximation? It is, in fact, it is very simple. Suppose we have two quantities. The first one is f, and the second one is g equal to 1 over f squared. 1 over f squared. Okay. So if we change f to f plus delta f, and g becomes g plus delta g is equal to 1 over f plus delta f squared. Okay? So, what is delta g? Delta g is this find this result approximately by using Taylor expansion or something like that. So this can be approximated by this 这样讲，就是你现在想象这个 delta f 远小于 f。Now, if delta f, the magnitude of delta f is much smaller than f, then this can be written as f squared plus 1 plus delta f over f squared 1. Okay? Then this can be approximated by 1 over f squared times对吧？因为这个二次方的太小了，这就是 f delta f 比 f 绝对是远小于 b， 所以它二次方那个不用管它，这边就分母这边就直接列成加2倍，但是你这个导数分式又会变成减的，所以它就会约等于这个。所以答案就会变成什么呢？这边消掉，消掉，就变成-2 delta f 除以 f 的30吧。So we see that if the value change very small, delta g can be approximated by -2 delta f over f cubic, which means that delta f can be written 1 over 2 minus 1/2 this times delta g. Okay, so here this is the f, this is f, this is g. Okay, so delta g here, this part is delta g. Okay, so minus 1/2 f cubic times delta g， 就得到这边，得到这个结果。所以如果是这个误差量很小的时候，就可以近似的写成这样。所以那这边减的时候，这个2次负号就变加了。So this is the result listed in 7.2-9 to 7.2-11。好，这个就是如果把电场加在地方上的时候。Now, how about we apply the electric field along the x direction? If now we apply the electric field along the x direction. Then now we have to consider this x squared over no squared plus y squared over no squared plus z squared over ne squared plus 2yz r for 1ex equal to 1. 那现在这个情况就比较麻烦了，因为呢，这交叉向 yz， 但是这边前面这个平方向呢 ，y 的系数跟 z 的系数不一样。好 ，Now the coupling term 啊 this term 2yz. However, the coefficient of y squared and the coefficient of z squared are different. This means that we cannot easily, as easy as we did before, then rotate 45 degrees to decouple this to get the quadratic term. Okay, so now we need to consider what angle we should use to rotate the coordinate axis to decouple this coupling term. Okay, so we know now we write down y prime z prime as r of theta times yz, and so we can write yz as r minus theta times y prime z prime, and this is cosine theta minus sine theta, sine theta, cosine theta, y prime z prime. Okay. So this means that y is equal to y prime cosine theta minus z prime sine theta. Okay, and z is equal to y prime sine theta plus z prime cosine theta. Okay, so now we need to calculate every term separately. Okay, so so y squared now is equal to y prime squared cosine squared theta plus z prime squared sine squared theta minus 2y prime z prime sine theta cosine theta, and the z squared is equal to y prime squared sine squared theta plus z prime squared cosine squared theta plus 2y prime z prime sine theta cosine theta. Okay, and and the yc and the yc is y prime squared minus z prime squared times sine theta cosine theta plus y prime z prime times cosine squared theta minus sine squared theta. Okay. You can substitute this expression into this formula. Then you encounter new mixing term like this. Some coefficient have this plus some square term. Okay. However, now our purpose is to diagonalize this equation. So this means that we must choose theta so that the coefficient of y prime z prime equal to 0. Okay. So this will give us the result about the angle. So that the result is that tangent to theta must be chosen so that it is equal to 2r41 ex over 1 over no squared minus 1 over ne squared。好，就说我们现在究竟要转多少角度，其实是看怎样让这个括号等于0。然后当我们要求这个括号等于0的时候，我会解出这个角度，这个角度的 tangent 就会长 tangent 2倍角的 tangent 就会长成这样。好，然后一旦这个东西知道了之后，我们得到这个角度关系之后呢，最后我们就会发现说，最后的那个形式的then the final result is this.或者最后这个会长这样，那就可以从这边去算出新的 nx 就是 no 没问题，新的 ny 会变掉，新的 nt 会变掉。好，那这个具体的细节我们下礼拜再讲。好，就这边先跟大家讲概念上就是这样。